Now, finding the area between curves, there's a few different ways we can go about this. I'll show you first the most basic way that we'd do it. I'm trying to find the area between the curve y equals x squared plus 3 and the curve y equals x plus 1 between x equals 1 and x equals 3. So here's x equals 1, here's x equals 3. I'm really trying to find this shaded area. If I was trying to do this just geometrically, the way I'd think about this would be, alright, the area, I'm going to find the area underneath the parabola, underneath that big curve. And then I'm going to subtract the area underneath the straight line. And that should give me the shaded area. So to find these two areas, since I know how to do definite integration already, would be integral between 1 and 3 of whatever that top function was, x squared plus 3 with respect to x, and then subtract the integral between those same bounds of x plus 1. Okay, we'll go ahead and perform this integration for practice. And then it'd be a case of evaluating at these bounds. I'll end up with 26 on 3 units squared. Don't have any units on either of these axes, so it's the best I can do. There is an alternative method where I can actually do the bottom equation minus the top equation and then integrate that new function. X squared plus 3 is the one on top, x plus 1 is the one below. So my new function will be the top equation minus the bottom equation. That is x squared plus 3 minus x plus 1, brackets because I'm subtracting more than one thing. I'll end up with x squared plus 3 minus x minus 1, or x squared minus x plus 2. So I've sketched that down here. That is x squared minus x plus 2. And I can integrate between 1 and 3 of this new function, and this shaded area will be the same as that shaded area above. Because what we're doing is we're looking at what is this height and putting it here. And then at 2, I'm looking at what's this height and putting it here. And then at 3, I'm looking at what's this height and putting it here by finding the difference of the height at all those points. Just to make sure this process works, I'll just verify this. The area will be the integral between 1 and 3 of this new top minus bottom function, x squared minus x plus 2. Perform the integration. And then substitute in the bounds and evaluate. So has this really saved us any time? Yeah, maybe a little bit of time. Instead of doing 2 integrations, we've only had to do the 1, and we've got the same answer. If we turn the page, we'll look at some examples where this top method really just isn't practical. Okay, again, I'll try to find the area between 2 curves here. I want to find the area between y equals 2x minus 5 and y equals x squared minus 2x minus 2. Okay, between x equals 0 and x equals 4. Okay, I'll get out my colouring in pen and show where that is. So between the curves and between those bounds. So I'm talking about this shaded area, because that's between the curves, and then talking about this shaded area, and then finally all the way up to 4, talking about this shaded area. If I was to try that first approach with this problem, I'd be in all sorts of trouble thinking, what am I subtracting from what? Getting negatives all over the place. So our preference will be to use that top minus bottom approach. When I subtract the top function, so I've got my top function as the quadratic, the x squared minus 2x minus 2, and my bottom function is the linear function with 2x minus 5. When I do this subtraction, I'll end up with x squared plus 4x plus 3. Okay, and it looks something like this. So I'm still trying to integrate between 0 and 4. So I'll get my colouring in pencil again. I'm still trying to find the physical area between 0 and 4. But I've got this problem that, like in the previous lesson, I've got some negative areas here. So I'm going to need to split this integral up into a few parts, okay, based on where it changes to a negative area. So the way I'm going to find these coordinates, these ones correspond to where the graph actually, where the two curves intersect. Okay, so before I even try to perform any integration, I'm going to need to find any intersection points between the two curves. I've got two equations, y equals 2x minus 5 and y equals x squared minus 2x minus 2. I need to solve these both simultaneously, equation 1 and equation 2. I'm going to let equation 1 equal, or sub equation 1 into equation 2, either way you want it. I'm essentially solving this equation for values of x. It's a quadratic. I know I need to set it equal to 0. Okay, and hopefully I haven't messed anything up here. Yep, I definitely have. So that should have been plus 3. I'll factorize. Okay, looking for two numbers that multiply to 3 and add to minus 4. So I'm thinking 3 and 1, but both of them need to be negative. So here are my two factors, x minus 3 and x minus 1. So my two x coordinates of the intersection points will be when x minus 3 equals 0 and x minus 1 equals 0. So when x equals 3 and x equals 1. So this is going to, and we can see graphically, yeah, looks pretty good. This is going to indicate to me the way I need to split up my integration. So to find the area, I'm going to be integrating from 0 to 1, from 1 to 3, and then from 3 to 4. And when I'm doing that, I'm going to be integrating this top minus bottom function. And since some of the areas are positive and some are negative and some are positive, I don't want to have to think about that too much. So when I'm finding the area, I'm just going to integrate between these bounds, between 1 and 3 and between 3 and 4. But I'm going to take the absolute value of each of these results. And again, I'm integrating the top minus bottom function. You might be thinking, how do I know which one's the top and which one's the bottom? It sort of switches over all the time. Answer is, it doesn't matter. If you get it the wrong way, it just means that instead of having, say, positive, negative, positive, you'll have negative, positive, negative. But when we take the absolute values, we'll get the same thing in the end. So I'm going to integrate away. I'm allowed to add since I'm going to be taking absolute values anyway. Okay, all the detail you can do on your own. Okay, so we'll notice that we get a lot of symmetry there. All of the areas are pretty much the same. Okay, one positive, one negative. I did make a little error here. I did have a plus there, so you'll have to Hopefully you recognize that and you've gone through and fixed all of those to negatives before you've substituted things in. Okay, again, the good thing about these absolute value signs is that if it's positive, it stays positive. If it's a negative value, it changes to positive. So in the end, I'll end up with 3 lots of 4/3, okay, which is 4. Surely that makes sense. Sounds good. Okay, so to conclude, area between curves, always do top curve minus the bottom curve, and you need to integrate between wherever there are intersection points on the original graph, which you need to find using simultaneous equations. Heaps of questions here to practice. You'll hopefully get really good at this skill. All right.